In this video, we'll discuss line integrals. So a line integral is just integrating a function or a vector field along a curve that is in the plane or in space. So the definition for a function, the line integral of a function f of xy defined on a smooth curve. Smooth for us means that it's given, this curve is given by a differentiable vector function. So defined on a smooth curve is denoted as follows. So the line integral of the function f of xy along a smooth curve C, so I should say defined on a smooth curve C, is denoted like that, and it's the limit of adding up the values of the function along the curve, taken along the curve with pieces of the curve and their arc length multiplying this value of the function. And this limit is taken as n goes to infinity. So you have to imagine having n points on the curve itself C. So we are chopping the curve up into, let's say, n pieces, and for each piece we take the value of the function along that arc or that section, and we multiply the value of the function with the length of that small piece. We add these up and take the limit as the number of pieces goes to infinity. So we approximate better and better the integral of the function along that curve. So that's our line integral of a function. But in practice, the way we compute such a line integral is using what we've learned about vector functions and curves, and in particular how the arc length can be computed using any parameterization of the curve. So remember that the arc length of a curve parameterized by a vector function with components xt and yt, with the parameter changing from a to b, is just integrating the length of the derivative of that vector function. For us, this means that we take the components x, t and yt, we differentiate them with respect to t, and take the sum of their squares of these derivatives under the square root. So that's the length of the derivative of rt, and we integrate that with respect to t with t changing from a to b. So that's the arc length formula, which we've seen before. And similarly, we've seen that the arc length function differentiated with respect to t is actually just what we have there in the integrand. So with this, we can actually change from integrating with respect to x, with respect to s, the arc length parameter, to any parameter t. So due to this formula, we can just reformulate this line integral in the following way. So we can evaluate the line integral of a function f of x, y along a curve C if that curve is parameterized by a vector function rt with components xt and yt, with t changing between a and b. So with this setup, this line integral can be evaluated by integrating with respect to t, with t going from a to b, f of xt yt multiplied by the square root of the square sum of the derivatives of x and y with respect to t dt. Okay, so this is a simple consequence of that arc length formula that we had before. So let me give you an example. So let's say that our function, so it is an example, our function is 2 plus x squared y, and our curve C is the upper half circle of radius 1 centered at the origin. Okay, so this means that xt is the cosine of t, yt is the sine of t, and t changes between 0 and pi over 2. Okay, so pause the video and evaluate the line integral of f along this upper half circle. Okay, I hope you paused it and used this formula to integrate between 0 and pi over 2 the function 2 plus x squared times y. So now x of t is of course the cosine of t, so that we have to square, so that's the cosine squared of t, times y, which is the sine of t along the curve. So this is our function that we need to integrate with respect to t, but we also need that have that extra factor. So let's just look at that. In this case, if xt is cosine of t and yt is the sine of t, then the derivative of x with respect to t is minus sine t, and the derivative of y with respect to t is the cosine of t. So in this case, this expression of dx over dt squared plus dy over dt squared under the square root gives us minus sine t squared plus the cosine of t squared. So that's by just the trigonometric identity that the sine squared plus the cosine squared gives you 1 is just equal to the constant 1. So here we have this constant 1, and then we integrate with respect to t. So integrating this function is not too difficult. The antiderivative of that function is 2t minus 1/3 times the cosine cube of t, as t changes from 0 to pi over 2. And when you evaluate that, you get pi from the 2t term, and you get plus 1/3 from the cosine term, and another plus 1/3 when you evaluate at t equals 0. So that's going to give you pi plus 2/3. Okay, so now we understand how to evaluate the line integral of a function. Now we can discuss the line integral of a vector field. And that is relevant because if the vector field is describing a force field, then the line integral along the curve gives you the work that is done by that force field while you move from a certain point, from the initial point of the curve to the end point of the curve. So that's that's the physical application of line integrals. Mainly it's computing work. So let me just mention that the line integral, so the definition of the line integral of a vector field, capital F, of xy is, well, along a smooth curve C, parameterized by, again, some vector function rt, with t changing from a to b. This line integral is integral of f, and it's the integral of the dot product of f and dr along C. So what this means is that we actually take the dot product of f, the vector, the vector field, and the unit tangent vector of the curve at each point, and this dot product is a number, is a function now, of which we can evaluate the line integral. So that, of course, in t parameterization means that we are integrating from a to b the dot product of f with along the curve, so xt, yt, and its dot product with the derivative of the vector rt parameterizing our curve. Then it is integrated with respect to t. So that's our formula for the line integral of a vector field along a curve. And so let me now give you an example, again, a question to take the vector field f of xy and the vector field that has x squared as its first component and minus xy as its second component, and let the curve C be now a quarter circle in the first quadrant of radius 1 as we go from the point 1, 0 to 0, 1. Okay? So pause the video and compute this line integral below. Okay, I hope you paused it and realized that this curve can be parameterized by the following vector function rt, that is the cosine of t I plus the sine of t j, as t changes from 0 to pi over 2. Okay. In the previous problem, I need to make a correction. So this, I said it's between 0 and pi over 2, but actually to get the upper half circle that I mentioned, t has to change from 0 all the way to pi. So this has to be pi, this has to be pi. Here we are going up to pi, but the result is only going to change with 2 pi being there. So that's a small correction I just realized. So here we really have a quarter circle, so t really just goes up to pi over 2 radians or 90 degrees. So that's our curve being parameterized. Of course, the derivative vector of that curve is the minus the sine of t I plus the cosine of t j. So we have r prime of t that we will need in this dot product with f. So as t changes between 0 and pi over 2, we have f. So that's x squared but remember we are computing it along the curve, and x along the curve is the cosine of t, so that's the cosine squared of t, and we have minus xy, so again along the curve x is equal to the cosine of t and y is equal to the sine of t. So this vector f is minus the cosine of t times the sine of t in the second component, and we compute its dot product with this vector that is minus sine of t cosine of t, and we integrate with respect to t. So this dot product is going to give us, in the integrand, is going to give us minus sine of t cosine squared of t, and again minus sine of t cosine squared of t, so that's twice minus sine of t cosine squared of t with respect to t, and the antiderivative of that function is actually plus 2/3 cosine cubed of t, as t changes from 0 to pi over 2. Okay, so at pi over 2 we will get the cosine vanish, but at t equals 0 the cosine function takes the value 1, so that is going to give us in the lower boundary minus 2/3 of the cosine of 0, so that's minus 2/3. Okay, I hope you enjoyed this video, and I'll see you in the next one.